Next we look on some techniques that are needed to use meta-heuristic search in software testing and to generate high code coverage. So to use the search-based techniques to generate tests that cover all execution paths, we need certain modifications and we need certain things inside the source code. So I'm just going to offer a brief look on those so that you understand how this works. So what is needed is that we have to have an instrumented version of the software and an execution monitor. So instrumented version basically means that you can modify the source code statements automatically, and you have to have an execution monitor to understand which source code lines have been covered. So this allows inside access to the execution of each line. Also, some other things are needed, like mock objects and other automated modifications. We also need cost and cost fitness functions for all the conditional statements. And the goal of this work is basically to generate test data or test cases that cover 100% of the execution paths. This is better testing. There are some regulatory domains that need this kind of test coverage. And as pointed out, in automated program repair, it is a great benefit to have test cases that cover all the different execution paths. So booleans, for example, represent a particular problem. So if we have A equals B type of thing, it is very unlikely, or it's a sort of a binary thing again. So A must be exactly B in order to hit some boolean, for example this first one. And it's a binary sort of on-off thing. So we need some type of approach, or we need to turn this binary thing to continuous thing. Because when this is a continuous, then we can measure it. So we need some type of fitness function for this equals case. So what is done here is that the source code is modified and we actually measure the absolute value between A and B. And once this absolute value hits 0, then also the cost is 0 and we have found our target. In all other cases, we measure the distance between A and B. So we have a fitness function that we can strive closer to A equals B. And this way we can use this as a fitness function to teach the genetic algorithm. And this is also extended to other booleans as well in this table. You see this mystical k here. It is basically needed as the non-equals case needs to have a cost as well. So this non-equals case is something that you hit pretty easily. So it is the obvious, it is the inverse of A equals B. So you basically hit it every time, but sometimes by just random chance you hit it. And now you need some type of cost for it, for the fitness function, so that you can strive towards the 0. So you must have some fixed cost in that for that case. And then this k is entered in here. And then it's also added to all the other cases to keep the costs similar between all the booleans. Okay, so this offers a sort of a cost for hitting the different booleans and having a fitness and cost functions for them. And this is also called branch distance, telling how far off you are hitting from a particular branch. And some other things that you also need is that if you have a nested code, the branch distance is not enough. So you must also keep track on how deep you are in the code. So you must also have another fitness measure, which is the approach level. So if the branch distance is the fitness function for a particular statement, how close are you hitting it, then you must also keep track on how deep you are in. So you try to get all of these to 0. So once you get some branch distance to 0, then you get, if you come out on this comparison, if count greater or equals to 4 as false, then your approach level is 1 and your branch distance is 4 minus count plus k. But if you match this condition, then the branch distance here is 0. So now you have hit the branch. But your approach level but you come out from this branch. So then your approach level has reduced by 1. So you must also keep track of this other measure in order to be able to handle nested code as well. Then also a bunch of other stuff is needed. For example, you can have classes, you can have interactions with the environment that you need to mock. For example, if you have a source code that handles some network operations, you might need some simulators and so on. And you would need to mock these sort of network connections as well. And also the Java library classes you sometimes need to mock. But many of the current tools can actually handle this. But this is just on some of the insights on what is actually needed inside the tools for them to be able to produce source code that covers 100% of all the statements and even 100% of all possible mutations to the source code. So this basically concludes my part of this lecture. There are some tools utilizing search-based techniques, and they are best introduced by the authors. So there are 2 videos for you to watch. One of them is from the Facebook engineers that are running the tool called Sapiens, and then there is a video about the EvoSuite tool by Andrea Arcuri. And the EvoSuite tool is the one that is also you will also try out during the course. So now you will learn a bit more details about how the particular tools work, and there is also some overlap with the things I have covered. So I thank you for this, and I hope you enjoy the 2 remaining videos.